My name is Fabian Tamayo. The work is correlation terms and water fraction distribution in HbA and HbS intracellular solutions. Okay, the NMRD profiles have been extensively used to study protein solution over the last 50 years. For rotational diffusion of dilute protein solution and not interacting on approximately spherical proteins, the evolution of longitudinal correlation times and versus the frequency is expected to have a Lorentzian dispersion. But this approach considers a fast exchange water molecules between the free and bound state, exponential autocorrelation functions, and a dipolar interaction between the proton inside the irrotationally bound water as the main contribution to water relaxation. When the concentration of protein is increased, the NMRD profiles is extended over a much wider frequency range than a Lorentzian dispersion, and this is called the stretched NMRD profiles. To fit these stretched NMRD profiles, convenient and physical plausible mathematical functions are being developed as Lindstrom and Koenig and Halenga and Koenig models have developed. But this function allows calculate or obtain directly the correlation time. Nonetheless, these physical plausible mathematical functions are not based on the theory of protomagnetic relaxation in protein solutions and giving not appropriate inference about the behavior of the physical system. In this work, we propose a three-site water exchange model to fit the NMRD profiles in intracellular hemoglobin solution, suggesting distribution of water fractions and correlation times. This is the usual stretched NMRD profile with using the two sites exchange model. The samples were obtained from wool blood from voluntary healthy donors and sickle cell disease patients from the ULB Brussels University Hospital, obtained after routine blood tests were finished. The samples were prepared using classical methods, and to obtain the NMRD profiles at 310 Kelvin, fast field cycling NMR relaxometer was used in the range from 20 kilohertz to 10 megahertz. And also additional points were added after measuring the samples in MQ20 and MQ60 NMR analyzers. For each sample, as less 5 NMRD profiles were measured, and the value of the correlation times was reported as follows, where X bar and S represent the mean value and standard deviation of the N measurements performed, and that is the T student parameter for 95% of confidence, alpha equal 0.05 and n less 1 degrees of freedom. Where that figures shows the typical NMRD profiles in samples of HbA and HbS for intracellular solution, and include the fit of experimental profiles using the method developed by Lindstrom and Koenig and Halenga and Koenig. We can see the goodness of the fitting, but the values of correlation times calculated from LK and HK models are coherent with those obtained in previous research, including EPR results using nitroxides radicals. Nevertheless, there are significant statistical differences between the correlation times for the same hemoglobin samples. On the other hand, the HK approach is node-based in the divide theory for the electrics as is usually assumed. And moreover, in this method, the dependence between the correlation times and the Khaled cut frequency is not theoretically supported. The most used theory for proton magnetic relaxation in hemoglobin solution is based in two sites exchange model, but this approach failed to fit the experimental NMRD profile. To solve this inconvenience, different suggestions have been made, including the presence of correlation times and or binding sites distributions. This is the two-state model with a distribution of 3 correlation times for the bone fraction of water. And this is applicable if you consider the hemoglobin as a revolution ellipsoid when where every correlation time corresponds with the rotation of the hemoglobin molecule around the three axes of that representation. When you analyze the obtained correlation times, we can see the similarity between the second and third correlation time, and that indicate the rotation of the hemoglobin molecule about around the similar axis of the shape or the of the representation of the revolution ellipsoid. And this model permit to obtain the fraction of water for this analyzed molecule. Another way to represent and fit these stretched NMRD profiles is using the three sites model suggested by Cotton and co-workers, where we have a fraction of bone water, a fraction of hydrated second layer of water, and free water. If we use that model, we can see inside the brackets the correlation times associated with that binding sites. The values of considering the values obtained with these results match with previous research and previous reports and are in the same order with the theoretical estimation performed. That results confirm the existence of a discrete distribution of correlation times, and this approach allows to evaluate the fraction of water associated to each binding sites, including bone water, hydrated water, and free water. Is plausible remark what consider more than 3 sites for water association to the hemoglobin could give place to even better results sometimes, but this approach is inconsistent and failed in the majority of the analyzed data for us, and decrease the number of the association sites is the case already presented with very bad results. The three sites model is already another way to characterize the dynamic of the water-protein interaction inside the hemoglobin solution. And it confirmed what have been suggested in the literature and by other authors. Conclusions, we have a correlation time and water fraction discrete distribution were obtained in intracellular solutions. A three-site exchange model was successfully used to fit the experimental profiles. And we have a quality of the fit comparable with those obtained with the most frequently used empirical methods. The most remarkable things is the goodness of the fit and we have a model based on the relaxation theory for the hemoglobin solutions. Thank you.